Question A asks, what is the number of tag, index, and offset bits used by the cache? So let's first look at what the problem tells us. We have a direct map cache here. I'll use a highlighter. We have a direct map cache here with 16 blocks. Each block holds 8 bytes, and memory addresses are 32 bits in size. So in order to calculate the offset size, we can plug in a formula, which is just log base 2 of block size, which will give us 3. A more intuitive approach is to kind of visualize all 8 blocks. That's a terrible drawing. Let's see. Oops. So here we have our 8 blocks, and we index them from 0 all the way up to 7. So as you can see here, we need 3 digits in order to index all 8 blocks. Therefore, we need 3 bits to represent the offset. Now, index is very similar for a direct map cache. Instead of having a block with 8 bytes, we now have 16 blocks in a cache. So we can plug into the formula here log base 2 of 16, and that will get us 4. Put that in here. And again, a more intuitive approach is to draw this out. And we start here with 0. And we go all the way up to 15. You need 4 digits in binary to represent all 16 blocks. Therefore, you have an index of 4 for the 4 bits you will need. Tag is the leftovers. So we were given here that the memory addresses are 32 bits in size. Since we already used 7 bits, that means the remainder must all be in a tag. Therefore, we have 25 because 32 minus 7 is 25. Hopefully that makes sense. Alright, now comes the hard part. Consider the following C code. Alright, so the first thing I like to do here when I encounter a problem like this is to kind of like visualize what's going on in these 2 for loops. Let's first concentrate here on loop 1. So in loop 1, we have I times n cols plus j is equal to I plus j. Now, the exact value that we put in here doesn't really matter. We can kind of ignore this. What's really important is that we access I times n cols plus j in the inner loop. So, because n cols is 8, we can just like literally substitute this with 8 times I plus j. Now, because j is incremented by 1 in the inner loop, you can kind of imagine this as like, let's say we have the grid here. We can kind of imagine this as like the pointer like going through the rows in like sequential order. So the one thing that you should note about this first for loop, or this first double for loop, is that there's good spatial locality. Now let's look at the second for loop. So again, it's very similar. Like I said, we don't really care about what happens with total. We don't even need to know that this number really exists. All this is important is we access I times n cols plus j. Again, this is A times I plus j. But the difference here is that I is in an inner loop. This means that when we increment I by 1, we increment the pointer here by 8. So whereas the previous one had good spatial locality, this thing here has terrible spatial locality because it jumps by 8 pretty much every single instance. This is probably going to be important later. Okay, so assume that array is cache aligned. That's almost always going to be the case for these problems. Assume also that the compiler places total I and j in register strand in memory. Alright, now we are asked to calculate the cache hit rate. So, looking here in loop 1, the good spatial locality is going to be really important. Because there's good spatial locality, when we bring in a block, we're probably going to be using the next item in the block in the next iteration of the for loop. So, because our block holds 8 bytes, this means that it holds 2 integers because one integer has 4 bytes in it. So when we draw this out here, we can kind of imagine the first, let's say, 3 rows of this grid. Let's see, 1, 2, 3, 4, 5, 6, 7. Let's just draw out what a block looks like. So this is a block, this is a block, and this is a block, and this is a block. So zooming in, let's say on this block here, we know that this first axis is always going to be a miss because we're pulling in a block. However, the second axis here is going to be a hit. Therefore, we're going to have a hit rate of 50%, and the only mistype we're going to be encountering is compulsory. We're not going to run into conflict misses or any capacity misses here, mostly because of the fact that we only access every single item once, and once we access it, we don't go back to it again. At least that's for loop 1. Now let's look at loop 2. So here in loop 2, let me just draw this out again. Let me draw 4 rows. 1, 2, 3, 4, 5, 6, 7. Okay. Here, we have the same blocks as before. However, we don't use the same spatial locality we used beforehand. Whereas here, we went in this order. 1, then 2, then 1. Oops. Back. Then 1, then 2, and so on and so forth. Here, we're going down in this order. 1 and 2, 1 and 2, 1 and 2. So here, you see, we jump from block to block without actually using any of these blocks. Or without using the second item of the block. That means that when we jump to the next item, if it isn't already in a cache, then it's going to be a definite miss. So, do we have enough cache space for any hits here? Let's look at how big the cache is. The cache is 16 blocks, and each block holds 2 integers. That means we can hold 32 integers total in the cache. However, here we clearly see that A has 64 integers. That means when you drag things into the cache here, in part A, let me just erase this. So, we imagine this is our grid. At a halfway point, we would have filled up the entire cache with the first half of the grid. The second half of the grid hasn't even been put into the cache yet, but it's going to replace the items in the first half of the grid. That means that we've hit capacity. So not only do we have a bunch of misses now, because of the fact that because we jumped in this direction here, all of our misses are going to be of the capacity type. I'm not sure if I explained this well. If you still have questions about this, you can just ask on Piazza after I post this video. But for part C, the answer is 0%, and the mistype is capacity. Some of you might be asking why it isn't a conflict miss. And an answer to that has to deal with the fact that if we were to make this cache a fully associative cache, we would still have the same issue. A conflict miss is a miss that occurs because the cache isn't fully associative. So a good barometer to use to determine if a miss is capacity or a conflict is imagine what would happen if there was a fully associative cache running the same code. If there still would be a miss there because the thing has been replaced, then it'll be a capacity miss. Otherwise, it'll be a conflict miss. Another good barometer that's slightly less correct would be to check if there's any other empty spaces when you have to miss. If you have empty spaces left in the cache and you're still missing, that's probably conflict miss. If there's no empty space in the cache when you're missing, then that's probably a capacity miss. Alright, now let's do part D. Part D is very similar to part A. The only difference now is that we have 32 blocks instead of 16 blocks. We are still storing 8 bytes, and I believe it's still a direct math cache. So here is very similar. Offset is still 3. Let's see, offset is still 3. Index here, because it's 32 instead of 16, is log base 2 of 2 times 16, which is equal to log base 2 of 2 plus log base 2 of 16. Is just equal to 1 plus 4 or 5. And tag will be what's left over. So 32 minus 8, that's equal to 24. So our tag will now be 24 bits. So now what's a cache hit rate when the loop 1 is executed? This one I'm going to kind of skim over because it's very similar to part B. Because even though we have a bigger cache, right, the same idea still holds. Because it's a cold cache, the first item is going to be a miss, and the second item is going to be a hit. So we can use the same logic we used in part B and state that because we pull in a block, then we use the next item in that block, and then we pull in a new block, our hit rate is going to be 50%. And the miss type is going to be compulsory. Now, part F is the fun part. The cache hit rate here, because the cache now has 32 blocks of 8 bytes, right? If we do the math, that's 32. That's 2 integers. So we have 30. So our cache will have 32 times 2, or 64 integers in it. I can now store literally the entire cache. Because we're still running the same code here. We're still running a code with 64 integers. By the time we run loop 2 here, after we run loop 1, all the items will have been moved into the cache. Therefore, for the answer to part F, that's 100%. And there's no mistypes. So, this is the end of question 5. If you have any questions about this still, feel free to ask in Piazza. I'll probably reply as promptly as I can. Awesome, and good luck with the midterm.